So if we discuss about the two most important features or properties that we expect from any protective device or protective relay, no matter whether it is an electromechanical, static or a numerical relay, the two most important requirements are the sensitivity and the selectivity. Well, sensitivity is something that deals with the magnitude of the actuating quantity. So let us suppose that if we have a protective device which is of overcurrent nature, it means that its actuating quantity is current and it is going to operate if it is measuring a value of current which is over the pickup value. So it's obvious that for its operation we are going to define a pickup value, and let's say that the pickup value is 1 ampere. It means that the relay is going to operate if it is measuring a value of current which is more than 1 ampere. So if it is measuring a value of current which is, let's say, 0.9 ampere or 0.95 ampere, or even if it is 0.99 ampere, then during that situation the relay is not going to operate. But what if it is measuring a value of current which is 1 ampere? So during that case the relay may or it may not operate, but it is, even if it is not operating, it is not questionable because it is on the boundary line. But at what value of current it is going to operate is something which shall be slightly above the pickup value. So if it is operating at, let's say, value of current which is 1.01, that is 1010 milliamperes, means if it is just operating at a value of just more than 10 milliamperes of the pickup value, we say that it is having no problem with its sensitivity, because 1.01 ampere is almost equal to 1 ampere. But if it is taking a value of, let's say, 2 ampere or 5 amperes, then we say that the relay is not sensitive, and under no situation we are going to accept that relay, or we are going to install that relay in the system, because it is simply going to damage the system. So this is something about the sensitivity of the relay. And well, the second topic is selectivity, which has to do something with the stability of the electrical equipment. And in this video we are going to discuss about the stability test. Well, stability test is done on all the electrical equipments where we implement differential protection. So noting down the electrical equipments where differential protection is implemented, the first one is the transformer, where we implement differential protection. Then we implement differential protection for generators, we implement differential protection for motors, we implement differential protection for short transmission line, and differential protection is implemented for bus bars as well. So in this video we'll be discussing about the stability test on transformers and generators, and once we know about the stability test of transformer and generator, we can easily carry out stability test on motors. And well, about short transmission and bus bars, we will be discussing about them in some other separate video. Well, in order to understand selectivity in a better way, I have just drawn a simple power system network in which we have a generator which is generating power, and it's obvious that it is not generating power at a very high voltage. So in order to transmit power to a long distance, what we do, we increase the value of that voltage, or voltage of that generated power, with the help of a transformer which is just added to this generator, and which is this transformer, and the name given to this transformer is GT, or the generator transformer. Now what it is going to do is it is going to increase the value of the voltage to a very high value. And now that power with a very high voltage is being added to this bus bar, and from this bus bar it is being transmitted to this end, and here we are stepping down the voltage with the help of these two transformers, and the name given to these two transformers is, let's say, it's power transformers. So this is power transformer 1 and this is 2, so I am marking this one as power transformer 2 and this one as power transformer 1. And from this end we can see that the power is being taken to the load at a low voltage. So we have a load connected at this end, and similarly we have a load connected at this end. Now let us suppose that there is a fault in transformer 2. So the fault is located at this point, and it's obvious that we have circuit breaker at this end, at this end for the transformer, and for this transformer we have circuit breaker at this end and at this end. So since there is a fault in this system, what it is going to do is it is going to draw power from all the connected sources. So what all are the sources connected to the faulty point or fault location? Is this generator which is connected to this faulty location. What it is going to do is it is going to feed fault current in this direction, which will flow through these two transmission lines. It will take up this path, and it will take up the path of transformer 1, which will be added to this low voltage bus bar, and again it will take up this path. So this division is totally on the basis of the impedance of both of these two transformers. and about these two bus bars, if they have a connectivity with the system. So if we have a system which is having a lot number of generators, transformers and transmission lines in it, and it is connected in such a way, they are also going to feed the fault. So the fault current will be flowing in this direction, it will come to this bus bar, it will get added up, and it is ultimately going to increase the flow of fault current through these two transmission lines, and it will be flowing in this direction. So just for example, let us consider that in order to provide protection to these two transmission lines, means this transmission and this transmission, and what we do is we introduce a circuit breaker which is going to give current to the relay, and in order to provide protection to this generator, what we do, we introduce a circuit breaker at this point. So it's obvious that there is a flow of current in this direction, then the CT secondary is also going to experience similar flow of current which is being fed to the relay. So the relay is experiencing an increase in its actuating quantity. So all the relays, that is the relay at this end, the relay which is employed or which is implemented for the protection of this generator is also experiencing an increase in current. The relay which is installed at this point is also experiencing an increase in the actuating quantity. The relay at this point, means for the protection of this particular transformer, is also experiencing an increase in current. So all the relays are in picked up condition, but which is the one that is going to operate for clearing the fault? It's obvious that all the relays have picked up, but none of them is going to operate. The only relay that is going to operate in this situation is the differential relay of this particular transformer. That is, the differential relay of transformer number 2 is going to operate in this situation. So differential relay of transformer 2 shall operate, and what it is going to do is it is going to give a trip signal to this circuit breaker, and it is going to give a signal to this circuit breaker. And once both of these two circuit breakers are in open condition, we can see that this faulty location is in isolated condition now. So once these two circuit breakers are in open condition, the system regains its stability and the fault is now isolated. So this is something how So this is how the selectivity of the relay operates, because every relay was in picked up condition. Even for this particular power transformer, that is power transformer 1, the relay might have picked up but it did not operate. It means that it was stable, and we justify by performing the stability test on the equipment. Let us just pick up this thing in a detailed way. Let us just suppose that we are just considering the two transformers. So, and this side is the system which we had just seen, so I'm just writing it as system, and here we have load connected at this point. So in order to implement differential protection for this particular transformer, what we are going to do is we are going to introduce two CTs in this way, and we have a relay at this point, and similarly here also we are going to have two CTs which will be connected in this way, and we are going to have a relay at this point. So if there was a fault, let's say the fault was at this point, it's obvious that it is going to draw fault current in this direction. The fault will be flowing in this direction. This transformer is also drawing the fault current which is coming to this bus bar, and it is flowing in this direction. So since there is a flow of current through this particular CT, in order to balance that, there will be a flow in secondary of the CT, and it will be having this particular direction. And for this side, the current will be flowing in this direction, and we can see that in this transformer's differential relay, means this relay, the currents are flowing in these two opposite directions, means the differential current measured by transformer 1 will be 0, and here we can see that there is a flow of fault current in this direction, so it will be allowing a flow of fault current in secondary in this particular direction, and here the current is flowing in this direction. So in order to balance that, the current will be flowing in this direction. So if this is the differential relay, both the sides current will be flowing in this direction, and in this case for transformer 2, the differential current will be, let's say it's I1 plus I2, where I1 is the value of this current and this is the value of I2. So since there was a fault in transformer 2, the differential relay of transformer 2 was only measuring the current, and differential relay of transformer 1 was not measuring any current. Now similarly, let us suppose that there was a fault on the bus bar itself. So suppose that there is a fault at this point, then it's obvious that we have CTs connected in this way, and here we have CTs connected in this way, and we have a differential relay, and we have a system at this point which is going to feed the fault. So this transformer is drawing the fault current in this direction, this is also drawing the fault current in this direction. During that situation, the fault will be flowing in this direction in the secondary side, and for this side CT it will be flowing in this direction. So it's obvious that if this is the differential relay, one side CT current is flowing in this direction, the other is flowing in this direction, the differential current will be 0 for transformer 1. For transformer 2, it will be having a flow, since the flow of current is in this direction, the secondary current will be flowing in this way, and here the current is flowing in this direction, so the secondary current is flowing in this direction. So for this relay as well, if one side CT current is flowing in this direction, the other is flowing in this way, so the differential current is going to be 0. So this is a fault which is outside the differential zone of the transformer, where differential zone means the zone between the CTs. So if we have a transformer at this point, what we do is we introduce two CTs. So the area between these two CTs, that is this CT and this CT, is defined as the differential zone. So if there was a fault at this point, means the fault was at this point which was outside the differential zone of the transformer, then during that situation the relay is going to measure a differential current whose value is 0, and it is not going to operate. So if there is a fault at this point, differential relay is not going to operate. During that situation, the backup overcurrent and earth fault relay for the transformer is going to operate, but the differential relay is not supposed to operate. And during the previous situation, we were seeing that the fault was taking place at this point, which was within the differential zone. That's why this transformer differential relay was operating, and its differential relay was not operating because it was outside its CT zone, or it was outside its differential zone. So taking our discussion to the behavior of differential protection relays for three-phase transformers, I have just drawn a simple three-phase transformer in which we have the primary winding connected in star, the secondary winding is connected in delta. And talking about the vector group transformer, well, you can watch my video on vector groups in three-phase transformers, but in this video I'll just find out the vector group transformer, and it will be something like, so this is connected in star. If I just assume that it is drawing a current at I at an angle of 0 degrees, this is going to draw a current which is I at an angle of 240 degrees. This is going to draw a current which is I at an angle of 120 degrees. Here the current that will be flowing is small I at an angle of 0 degrees. Here it is small I at an angle of 240 degrees, and here it is small I at an angle of 120 degrees. So for this particular line, we can see that the current that is coming is nothing but it is I at an angle of 0 degrees minus I at an angle of this current. So this value is 120 degrees. So this is 120 degrees. So it is I at an angle of 0. This is 240 and this is 120 degree. So negative of 120 is something like this. This is 0, this is negative of 120, so the resultant will be something somewhere here, and it is minus 30 degrees. So minus 30 degree is implemented for the transformers one vector group. So the vector group of the transformer is YND1. Well, in order to understand all these calculations in a better way, you can just watch my video on vector group in three-phase transformers. But for the time being, we have already derived that the vector of the transformer is YND1. Now let us see how the differential relay is going to behave, or how it is going to be stable. So it's obvious that the vector of the transformer is YND1. So if the current is here, let's say I at an angle of 0 degrees, let's say it's capital I at an angle of 0 degrees, here it is capital I at an angle of 240 degrees, and here it is capital I at an angle of 120 degrees. So here in this line, the current value will be small I at an angle of minus 30 degrees. Here the current that will be flowing will be small I at an angle of 240 minus 30 will be 210 degrees. And here the current value will be small I at an angle of 120 minus 30 degrees is 90 degrees. So these are the values of phases that the current will be having during normal loaded conditions. Now in order to do this balancing, means here we are getting a value of 0 degrees, here we are getting minus 30 degrees, what we are going to do is we are going to connect our CTs in delta formation. On the star side and on the delta side, the CTs will be connected in star fashion. So let us suppose that on both the sides the current is same. So the flow of current in CT secondaries located on the star side of the transformer will be such that the flow of current is having this direction for the primary. In the secondary, the current will be flowing in this direction, and this direction. And it's obvious that all of them are going to have a phase shift of 0 to 40 and 120 degrees respectively. So the current that will be flowing in this line will be something like, it is this current minus this current, because this current is coming in this way. So magnitude or angle of this current is, let's say it's small c at an angle of 120 degrees, and here it is small c at an angle of 0 degrees. So the current that is flowing in this line is small c at an angle of 0 degrees minus small c at an angle of 120 degrees. This value will be equal to root 3 times of c at an angle of minus 30 degrees. So the current that is flowing in this coil is root 3 times of C at an angle of minus 30 degrees. And here also we are seeing that the current that will be flowing is, let's say it is having a magnitude of D at an angle of minus 30 degrees, because the current which was flowing in primary was having a phase shift of minus 30 degrees. So there is no change in phase shift because it is connected in star, but it is not having this direction because during normal condition the transformer primary is showing current in this way and the secondary will be supplying load in this way. So in order to balance that current, the current in secondary was flowing in this direction. So the direction of flow of current was something like this. So similarly here also, in order to balance the flow of this current in this direction, the current will have this direction. So the current will be coming in this way and it will flow this way. So it is D at an angle of minus 30 degrees, and we use intermediate CTs in order to equate root 3 times C equal to D, which is a very complicated task which I'll be discussing when I'll be making videos on differential protection with the help of electromechanical relays. But for the time being, let us assume that root 3 times C is equal to D. So with the assumption that root 3 times C is equal to D, we can see that they are having the same phases. Here the phase was minus 30 degree, here also minus 30 degree. So ultimately they have opposite directions. So the current that is flowing through this coil is ID is equal to 0. So during normal condition, this is how we say that the relay is stable, or this is how we check the stability of the relay, or this is what we expect from a relay during normal loading conditions. So this is how the differential relay of the transformer is supposed to behave when there is a fault outside the differential zone of the transformer, or when there is normal loading in the transformer. But how the relay is going to behave when there is an internal fault in the transformer? Well, in order to see that, let us take our discussion to numerical relays because it is easy to understand. So talking about differential protection of three-phase transformers with the help of numerical relays, this is how the circuit will look like, and this one represents the numerical differential relay, which I am marking it as 87. And the circuit is quite simple as compared to the previous one, or the traditional differential protection circuit, but since this is a microprocessor based relay, we are supposed to give a lot number of information to the relay regarding the transformer. So let us see what all are the primary informations that are to be given to the relay. So regarding the primary information that should be given to the relay, these all are the informations that we have to give. And the first one is MVA rating, that is the MVA rating of the transformer. So for example, let us consider that the MVA rating of the transformer is 80 MVA. Then we have to give information regarding the HV side rating of the transformer, or HV rating of the transformer. So let's assume that it's 220 kV and the LV rating is, let's say it's 33 kV, and the other two and the next two are HV side CTR and LV side CTR, which means the high voltage side CT ratio and low voltage side CT ratio. So the CT ratio of all these CTs which are lying on the HV side, if we are marking this one as HV and this one as LV, so this one is the CT ratio of all these three CTs is the HV side CT ratio and or HV side CTR, and this all are LV side CTR. So for example, in this case, let us just consider that the HV side CT ratio is 400:1 and the LV side CT ratio is, let's say it is 1500:1. And then we have to give information regarding the vector group of the transformer. So the information regarding vector group is needed because here you can see that the HV side CTs, or the CTs which are lying on the star side of the transformer, are connected in star fashion only. But in the previous figure, as we had seen, that CTs which are lying on the star side, they were to be connected in delta in order to have proper phase matching, because if the current is having a phase shift of 0 degrees at this point, here the current will be having a value or phase value of minus 30 degrees. So with this particular connection, we are not able to achieve phase matching, but that is done by the relay once we give information to the relay that the vector group of the transformer is what it is. Like in this case, the vector group is y and t1. So once we tell the relay that the vector group of the transformer is y and t1, it is going to take care of the phase compensation, and we are not to worry about all those connections. Or so apart from all these informations, we have to give one information regarding the CT connection as well. So we have to give information regarding the CT connection of HV side CT, and we have to give information regarding the LV side CT. So we have two options available regarding the CT connection, and the first one is standard and the second one is opposite. So from this figure we can say that the CT connection for the HV side CT is standard. So here the option that will be selected is standard one, and for the LV side CT as well, the option is standard one. So we are saying it as standard because in this CT we can see that the neutral is formed by shorting all the terminals which are lying towards the transformers. So here we can see that all these three terminals are shorted and they are grounded, and all these terminals are lying on or lying towards the transformer. So instead of shorting all these three terminals, we could have shorted these three terminals and formed a neutral, but in that case opposite option was to be selected. Now similarly on the HV side, we can see the CT secondary terminals which are lying towards the transformer, that is this terminal, this terminal, this terminal, they are shorted to form the neutral. That is why for the HV side CT also the connection pattern or the connection is in standard format. So this is about the information regarding the CT connection which we have to give to the relay. And after getting all this information, the relay is going to do some calculation on its own. So what the relay is going to do is it is going to find out, or it is going to calculate the HV side line current. So HV side line current will be nothing but it will be 80 into 1000 divided by root 3 into 220 kV, or it's simply 220, which will be equal to roughly around 210 amperes, and the LV side current rating will be similarly 80 into 1000 divided by root 3 into 33, which will be roughly equal to 1400 amperes. And the next calculation is HV side matching factor, which is called as K1. It is also known as amplitude matching factor and LV side matching factor, that is K2. Now why do we need to do all these two calculations is because let's just consider that the transformer is loaded, and it is loaded to 80 MVA. So the loading on the transformer is 80 MVA. It means that the current that the primary will be drawing is around 210 amperes, and the secondary line current will be around 1400 amperes. So here we had said that the CT ratio was 400:1, and here the CT ratio was 1500:1. So the current that will be coming in this line is it will be equal to 210 divided by 400, which will be equal to its 0.525 amperes approximately. And here the current that will be coming in this line will be equal to 1400 divided by 1500, which will be equal to 0.933 amperes, that is 933 amperes. So here the magnitude of the current that will be equal to 0.525, and here the current will have a magnitude of 0.933. So now we can see that the relay is measuring a current whose amplitude is 525 milliamperes, and on the other side it is measuring an amplitude whose value is 933 milliamperes. So even if the relay is taking care of phase compensation, if we are giving the information regarding the vector of the transformer, if we are not going for amplitude compensation, then it is always going to measure a differential current. So there will always be a current flowing in the differential coil, or it is going to measure a differential current, and the relay is going to operate. Thus it will never allow the transformer to come into service if differential protection is in service. So this amplitude matching is done by these two factors, which is calculated internally by the relay. And how it is going to calculate is the formula for K1 is it is the HV side CT ratio divided by the HV side rated current. So HV side CT ratio is 400 divided by HV side rated current is 210 amperes. So K1 will be equal to 400 divided by 210, which will be equal to 1.904 approximately. And similarly for K2, it is LV side CT ratio divided by LV side rated current. So it is 1500 divided by 1400, which will be equal to 1.071. So now from these two values, what relay is going to do is for every point, or for So now from these two values, what relay is going to do is it is going to calculate the differential current and restraining current. Now the formula for differential current is ID is equal to I1 into K1. Obviously you have to give a vector over it, and here I2 into K2 with a vector sign over it, and differential and restraining current will be equal to just the magnitude of I1 K1 plus I2 K2 divided by 2. So these are the two values, that is differential current and restraining current are the two values that the relay will be calculating every time, and it is going to locate the point on differential restraining graph. So it will be something like this. On x-axis we are having restraining current, and on y-axis we are having differential current, and we are going to provide settings to the relay. So we are going to provide setting to the differential relay. It will be having a curve like this. So every time it is going to find out the differential current and restraining current, and if it is saying that on the graph it is located somewhere here, so if it is having this much of differential current value and this much of restraining current, if it is lying in this region it is not going to give any trip. But if this point is coming somewhere here, so here we can see that the differential current has increased but the restraining current has reduced, then in this case it is going to give a trip. So this one is called as the tripping area, or the area above this curve is defined as the tripping area, and the area below is defined as the blocking area. So this is what the relay does every time, and let us see what the relay is going to do if it is just measuring a through fault or it is normally loaded. So during that situation, so taking an example of that situation when there is a through fault, let us assume that there is a dead short circuit at this point, and the amount of current that is flowing or it is drawing is, let's say, 2800 amperes. So the HV side of, so the LV side of the transformer is drawing a current of 2800 amperes. So it's obvious that the LV side will be drawing a current whose value will be 420 amperes. So this is how 420 amperes will be flowing in all the three phases, and the direction of current flow will be something like this, and here it will be flowing in this way. So the current that will be flowing in this line will be equal to 420 divided by 400 amperes, which will be equal to around 1.05 amperes. And on the LV side, the current that will be flowing will have this direction, means it will be taking up this path, and its magnitude will be equal to 2800 amperes divided by 1500 amperes, which will be equal to, it will be having this direction, and its magnitude will be equal to 1.866 amperes. So we can see that this current is having this direction, this way it is entering in the coil, and this way it is returning to the system. So this will be equivalent to all the three phases, or this is applicable to all the three phases. I am taking only one phase for simplicity or for understanding, but this can be applied to any of the phases. And for this side, it will be having this direction of flow, and this way it is returning. So we can see that this current and this current, both of them are opposite to each other. In this one it is entering in this way, and here it is leaving the point. So we can say that if this one is having a magnitude of I1 and this one is having a magnitude of I2, so the phase difference between them will be 180 degree. So if we are marking I1 is having a phase of 0 degrees, then I2 is going to have a phase of 180 degrees. So now about the magnitude of differential current, what it is going to do is it is going to use these two values, that is K1 and K2, and it is going to calculate the differential current. So differential current is nothing but it is I1 into K1 with a vector over it, and I2 into K2 with a vector over it. So I1 value is 1.05 and K1 value was 1.904. So 1.904, and since I2 is having 180 degree phase, so instead of this plus, what we can do is we can simply give a minus at this point, and magnitude of I2 is 1.866 and magnitude of K2 is 1.071. So it is 1.071. So ID is equal to, so we can see that ID is almost equal to 0. And now regarding the value of IR, it's having a formula of I1 into Q1 with a modulus at this point, and then it is I2 into K2 with a modulus at this point, and the total is divided by 2. So it's obvious that its value is going to be 2, so IR will be 2 in this case. And with this value, that is ID is 0 and IR is equal to 2, the location of the point on this curve will be somewhere here. So if we are having IR on this point on this axis and we have ID on this axis, and this is the setting for the relay will be, the operating point will be somewhere here. So if this is IR is equal to 2, the point will be located at this point, and we can see that it is below the setting point, or it is lying in the blocking zone. So even if there is a fault, it is outside the differential zone of the transformer. The relay is seeing it as a fault in its through fault zone. That's why its differential current value is 0 and restraining current value is high. That's why the relay is not giving any differential trip signal. So now let's take an example when there is fault internal to the transformer or within the differential zone of the transformer. So the fault is three-phase fault and it is located at this point. Then during that situation, it is going to draw a current in this way. And let us assume that the fault current was 2800 amperes. So in this case, it may not be 420 amperes, but let us assume that from this side, the current that was flowing was 420 amperes. So now we can see that for this side CT, the current is having this direction now. So in this case, we can see that both the coils have the current flowing in the same direction. So if I1 is 0, I2 is also going to be 0. So ultimately what will happen is that previously what we had a negative at this point will now change into positive, and ID, which was 0, will now become 4, and there is no change in restraining current, so it will remain 2. So the location of point on this curve or on this plot will be somewhere like, if IR is equal to 2, ID will be 4 at this point, and it will be located somewhere here, which is lying in the tripping zone of the transformer. Thus the transformer will issue a differential trip, and this is what the relay is supposed to do. Means it is going to give, or it should give, a trip signal if there is a fault within the transformer, and it shall remain stable if there is a fault outside the differential zone, or if there is a fault at this point. But there are certain cases when the relay is supposed to maloperate. Means this relay gives trip signal to the transformer, or this relay senses it as a fault within the differential zone even if there is a fault at this point. So this is something which is not desired, and the next line of action is to perform the stability test on the transformer. So this is the point at which we are going to perform stability test on the transformer to justify that there is no problem with the differential protection circuit of the transformer, or to check what is the problem lying with the differential protection circuit of the transformer. So now let us take our discussion to the topic of stability test, or how we are going to perform stability test on the transformer. So basically stability test is nothing but it is short circuit test carried out on the transformer. Now let us see how are we going to do, or how are we going to perform the stability test on the transformer. And in order to perform the stability test, what we are going to do is we are going to perform a short circuit test, which we are going to do in this way. So we are going to short all these terminals, or we are going to short the terminals after the CTs, and from the other side we are going to apply a low tension AC voltage. So these are the three terminals which are extended, and across these three terminals what we are going to do is we are going to apply low tension AC supply, so which will be around 420 volts, because on the magnitude of this volt, the magnitude of current that is being drawn by the transformer is determined. Actually it has relationship with the percentage Z of the transformer. So for this particular case where the MVA rating was 80 MVA, if we say that the percentage Z of the transformer is 5%, it means that during such situation when there is a short circuit on one side of the transformer, then if we apply 5% of the rated voltage, so in this case we are applying voltage from this side, so this is the HV side, which is 220 kV. So if we are applying 5% of 220 kV from the HV side, and if LV side is in shorted condition, then HV side is going to draw a current which will be equal to the rated current. So in this case the rated current is 210 amperes. So 5% of 220 kV is nothing but it's 11 kV. So during short circuit condition, if 11 kV is applied, the current drawn will be 210 amperes. But low tension AC value is 420 volts. So in that case, the current that the transformer will be drawing will be 210 into 420 divided by 11 kV, which will be roughly equal to 8 amperes. So the magnitude of all these currents will be around 8 amperes. So here it is 8 amperes, 8 amperes, 8 amperes, and this side the current that will be flowing will have a magnitude of 8 into 220 kV divided by 33 kV, which will be roughly equal to 53 amperes, or it is 53.3 amperes. So we are just saying that it is 53 amperes. Now 8 ampere will be stepped down with the help of this current transformer, and it will be fed to the relay, and here this 53 ampere will be stepped down with the help of these three current transformers, and it will be fed to the relay. So here we can see that the magnitude of current in all these three lines will be equal to 8 divided by 400, and here it will be magnitude of current in all these three terminals will have a direction of current flow in this way, and here it will be flowing in this way. So in this line the current that will be flowing for all these three terminals, means in this one and this one, will have a magnitude which will be equal to 53 divided by 1500. Here the magnitude will be around 220 milliamperes, and here it will be 53 divided by 1500 will be equal to 35 milliamperes. So here it is 35 milliamperes. So this is what is the value of current that we are going to measure. So once we perform the short circuit test, what we are going to do is we are going to apply low tension AC from this end. It is going to draw this much of current, and based on that CT ratio we are going to check that the CTs are drawing this much of current or not, or means the current flowing in all these three lines shall be equal to 20 amperes roughly, or it shall be plus minus 2 or 3 milliamperes, means it shall be around, it should be around 18 to 22 milliamperes, but not more than that. And in this line the current that is returning shall be approximately equal to 0 milliamperes. So the current that will be returning will have this direction of flow, and it will be equal to 0 milliamperes, but it is not generally 0. It may have a value of 1 or 2 milliamperes. So 1 or 2 milliamperes is acceptable, but we cannot allow a flow of 10 to 15 milliamperes when the voltage applied is just 420 volts. Similarly, here we can see that in all these three cases the relay is going to, or the current that is going to flow in all these three wires will be roughly equal to 35 milliamperes, here also 35 milliamperes, and here also 35 milliamperes. And we are going to see the reading by the relay. Means from the front panel of the relay we can see the differential current that is being read by the relay, and we can see the restraining current that is being read by the relay. So during this particular situation the relay is going to read a differential current which is going to have a value of 0, and it is going to have some value for restraining current. So let us just say that it is XYZ. So this is what the relay is supposed to show. So these all are the readings that we are supposed to get when we are performing stability test on this particular transformer with this much of voltage ratio, if we have 5% of percentage impedance. And similarly here as well, in this line also we are going to measure a current which is going to have a value of 0 milliamperes. So 1 or 2 milliamperes is okay, but we cannot allow 10 to 15 milliamperes of spill current during such a faulty condition. But what if we are not going to get, but what if we are not getting all these values, means the values are not identical, then it simply means that there is some problem with the differential protection circuit. So there might be a problem with the CT. So what we are going to do is we are going to test this CT, this CT, and this CT. And similarly, we are going to test all these three CTs on the LV side of the transformer. And if CT test is okay, then there might be some problem with the cable. So we are going to do the insulation resistance of this cable, this cable, this cable, and this cable. And in order to do that, what we are going to do is we are simply going to remove this grounding where we have a link. So there will be a link. After opening this link, we can see that the system will be ungrounded. We are going to perform insulation resistance test with the help of a 500 volts measure. So we will be performing insulation resistance test of all these four sets of cable on the HV side of the transformers, and the same thing will be carried out on the LV side circuit as well. So we are going to remove this earthing, and we are going to perform the IR insulation resistance test of this cable, this cable, this cable, and this cable. So even if there was no problem found in the CTs, means the CT test results had revealed that the CTs were healthy on both the sides of the transformer, the insulation resistance test says that the insulation resistance of all the cables which are coming from yard to the relay are healthy, then there might be some problem with the relay itself. So in the end, what we are going to do is we are going to do relay test, where we will be performing various tests which include pickup test, and then we are going to test the bias test of the relay, regarding which I'll be discussing in some other separate video. So these are the values that we are going to measure, or we are going to get when we are performing stability test on this transformer in this way. So in all these three cables, we are going to measure a current whose magnitude is 20 milliamperes. And this neutral, we are going to measure a current whose magnitude is 0 milliamperes. Here also we are going to measure a current whose magnitude is 0 milliamperes. And in all these three phases, we are going to measure a current whose magnitude is 35 milliamperes. So we are going to get all these readings or all these values for this particular transformer, means the transformer whose MVA rating is 80 MVA, whose voltage ratio is 220 kV by 33 kV, and of course its percentage Z is 5%. So I have taken 5% as the percentage Z of the transformer just for the sake of simplicity, but for this particular power transformer, means the power transformer whose MVA rating is 80 MVA, the voltage ratio is 220 kV by 33 kV, or even if it is 132 kV by 33 kV, the percentage Z normally lies in the range of 15% to 20%. So for this particular transformer, if we assume that the percentage of the transformer was 15%, then in that case the values are going to get changed. So previously, when the impedance was considered to be 5%, the current that was flowing was 8 amperes. Now it is going to get reduced because the impedance has now increased. So since the impedance has increased by a multiple of 3, the current is going to reduce by a multiple of 3. So the current that will be flowing will be 8 by 3 in this phase. Here also it will be 8 by 3, and here also it will be 8 by 3, which is equal to 2.6 amperes. So for this phase also it's equal to 2.6 amperes, and here also it is going to be 2.6 amperes. Now this current will be stepped down by all these three CTs, and it will be fed to the relay with the help of these three cables. Now the current that the current that will be flowing in all these three cables will have a magnitude which is equal to 2.6 divided by 400, which is around 6.5 milliamperes. Now 6.5 milliamperes is not that a high value of current that its measurement is easy. So measurement of such a small amount of current is not an easy task if we do not have an accurate tongue tester, or if we are not carrying an accurate ammeter. So for this particular case, if we assume that we were carrying a tongue tester whose accuracy was 10 milliamperes, then the measurement was not possible, because that tongue tester is not going to measure accurately if the current magnitude is below 10 milliamperes. So if the current was having a magnitude of 6.5 milliamperes, there is a probable chance that the tongue tester is going to give a value of 0 milliamperes. So even if there was a flow of current in all these three phases, we were going to measure a current whose magnitude is 0 milliamperes, which is just because of the accuracy limitations of the measuring device. So if we have such kind of measurements, then the next question is that how are we going to perform stability on this particular transformer? Well, we have the second option of performing the stability test, and it is that we are going to perform stability from the reverse side or from the opposite side. So in that, what we do is we perform stability test from the low voltage side of the transformer. So what we do is we apply low tension AC from this side, and what we do is we just short all these three terminals. So in this case, what happens is that we are going to have different readings. Now let us see what all readings we are going to get if we are performing stability test from the low voltage side of the transformer. So this is the transformer, and what we are going to do is we are going to perform stability test from the low voltage side of the transformer. So what we are going to do is we are going to short all these three terminals onto the CT, and we are going to apply a low tension AC at this end. So the value of that voltage is going to be 420 volts. And if we assume that the percentage rate of this transformer is 15%, and the MVA rating is 80 MVA, and its voltage ratio is 220 kV with 33 kV, so from percentage Z data, it is clear that 15% of 33 kV is going to allow a flow of 1400 amperes of current if the high voltage side of the transformer is shorted. So all these three phases are going to draw or extract a current whose magnitude is 1400 amperes from the source if the source had a voltage of 15% of 33 kV. So now if the source has a voltage of 420 volts, then the amount of current that they are going to draw will be equal to 420 into 1400 divided by 15% of 33 kV, that is 15.15 into 33 kV, and its value is roughly around 118 amperes. So the current that they are going to draw from the source will have a magnitude of 118 amperes for all the three phases, and here also it is 118 amperes. Now this side, Based on the transformation ratio, the current that will be flowing in this side will be equal to, it's 118 into 33 divided by 220 kV, which is roughly equal to 17 amperes. So now if the current that is flowing here is 17 amperes, so the step down current will have magnitude, or the current that will be flowing in all these three phases will be equal to, it will be roughly equal to around 43 milliamperes. So now we can see that if we are performing stability test from the low voltage side of the transformer, the amount of current that will be flowing in the circuit has now got increased. So this side it is 43 milliamperes, and here also we can similarly see that the magnitude will have a value which is equal to 118 divided by 1500. So here also the magnitude has got increased. So if the current that is flowing in the circuit has got increased, it's obvious that the accuracy of measurement will also be proper, or we are going to have accurate measurements. But while performing stability tests from low voltage side of the transformer, we have to keep one thing in mind, and it is that the capacity of all these three cables which are coming from the source to the transformer, they should be such that they can easily allow a flow of current whose magnitude is 118 amperes. Because if it is not proper, or if it is not such, then what will happen is that ultimately they are going to melt down due to the heat that is caused due to flow of such a high value of current, because 118 amperes current is not a small amount of current. So it is going to cause a lot amount of heat in the cable through which it is flowing. So this is how we perform stability test from the low voltage side of the transformer in order to have proper and accurate measurements. In the next video, we will be discussing about certain issues related to the stability test of the transformer, and then we will be discussing about stability test at generating stations, which include the overall stability of the generator transformer, stability of the generator, and stability of the UATs, that is unit auxiliary transformer. And then in some other video, we will be discussing about the stability of the REF protection, that is restricted earth fault protection, or zero sequence stability of the transformer. But in this video, we are stopping at this point.